Hi there, this is Momentum Concepts, Conservation of Linear Momentum. This is the third lesson in the Momentum series. So let's have a look. So conservation of linear momentum, you may wish to take some notes here. The total linear momentum of an isolated system of bodies remains constant. An isolated system is one where no external forces, example friction or air resistance, acts on the interacting bodies. So what this means is that the linear momentum before a collision will be equal to the linear momentum after the collision. And what we can do is apply that principle to questions. So let's have a look. So an example question. So if you've already done momentum, you might wish to have a go at this. If not, I'm going to show you a technique and then you can have a go at subsequent questions after this one. So this question, a trolley of mass 4 kilograms moving at 5 meters per second collides with another initially stationary trolley of mass 3 kilograms. If after the collision, the trolleys move off attached together, calculate their common final velocity. So I'll show you how to do this and how I would say it out. So what we can say is we can apply the conservation of linear momentum. So we can say that before the collision, the momentum, so the before momentum is equal to the momentum afterwards. Then we can do this, make like a grid. And then just check the momentum of everything. So before the collision, we have the trolley of mass 4 kilograms moving at 5 meters per second. So 4 times 5 gives a momentum of 20 for the first car. In fact, what I'll do is to make this, I'll draw a diagram as well. So we've got a trolley, initial trolley, 4 kilograms, and its velocity is 5 meters per second. Just sketch this out. And then we've got the second trolley that's got a mass of 3 kilos but is actually not moving. So obviously its momentum will be 0. And then after the collision, they join together. So if they join together, we need to combine the masses. So that's 7 kilogram mass. And an unknown velocity. So let's do the momentum of everything. So the first wagon, so 4 times 5 gives us 20. Plus 3, this one's not moving, so 3 times 0 is simply 0. And then we've got 7 lots of V. So essentially 20 equals 7V. Therefore, the velocity is simply 20 divided by 7. And 20 divided by 7 is 2.9 meters per second. So that's basically it. So we just need to do some more examples and make sure that we can do these types of questions. So let's move on. So if you want to have a go at this, just pause and then I'll take you through the answer. So question 2, a train wagon of mass 800 kilograms moving at 4 meters per second collides and remains attached to another wagon of mass 1200 kilograms that is moving in the same direction at 2 meters per second. Calculate the common velocity of the wagons after the collision. So this is very similar to last time. It's the same technique as question 1, but this time the second wagon is moving, whereas in the first example it was stationary. So if you want to have a go at this, please do, and then I'll take you through the answer. So let's sketch this out. So I'm going to write momentum before the collision is equal to the momentum after the collision. Momentum after. Draw a line. Make a grid. So first of all, we've got the train wagon. So it's 800 kilograms at 4 meters per second. I'm just going to write these out. 800 at 4 meters per second. Plus the momentum of the second wagon, which is 1200 times 2. 1200 times 2. And then afterwards, they combine. So we need to combine the masses. So the combined mass is 2000 times V. If you want to calculate this and finish off, just pause. If not, 800 times 4 is 3200. Plus 1200 times 2 is 2400. Equals 2000 lots of V. You'll notice that the equal signs just reside on the center line. So 3200 plus 2400 is 5600. Equals 2000 lots of V. So V is simply 5,600 divided by 2,000, which gives us a velocity of 2.8 meters per second. Hopefully that went okay. So let's have a look at the next one. So a bit of information, elastic and inelastic collisions. So in an elastic collision, kinetic energy is conserved along with mass, momentum, and total energy. So everything is conserved in an elastic collision. And then an inelastic collision, some or all kinetic energy is transformed into thermal or other forms of energy. So what's conserved in an inelastic collision would simply be mass, momentum, and the total energy. But the kinetic energy is not conserved. So the difference is between an elastic and inelastic is the kinetic energy being conserved or not. So like I just said, in both types of collision, both the total energy and momentum are conserved. So for the previous question, what I want to know is, was the collision elastic or inelastic? So I'm going to go back to the question in a moment, and what you need to do is apply the kinetic energy equation, the half mv squared, and figure out whether the collision was elastic or inelastic. So here we go. Let's do kinetic energy before and after. So I'm just going to do before. So we had the train wagon, 800 kilogram at 4 meters per second, so half mv squared, so that would be a half times 800 times v squared, so 4 squared is 16. Plus we would also have the kinetic energy of the other wagon, so that would be a half times 1200 times 2 squared, which is 4. And then we just need to calculate both of those and add them together to give the total kinetic energy before the collision. So we get 6,400 joules and 2,400 joules. And if we add them together, we get total kinetic energy before of 8,800 joules of energy. Then we just need to compare to afterwards. So after, we've got the same equation. So it's a half mv squared, so it's a half times the mass. The combined mass is 2,000 kilos. Multiplied by the common velocity afterwards, which we calculated to be 2.8 meters per second. So 2.8 squared. And that gives us 7,840 joules. So as you can see, the kinetic energy afterwards is less. Therefore, we have an inelastic collision. Okay, let's move on. So if you want to have a go at this, please do. Just remember that momentum is a vector quantity. So you have to pick one direction as positive and opposing direction will be negative. So a car of mass 1,200 kilograms traveling at 20 meters per second collides head on with a lorry of mass 3,000 kilos traveling in the opposite direction at 4.5 meters per second. The vehicles attached together calculate their common velocity after the collision. So we've got the 1,200 kilogram mass traveling at 20 meters per second, colliding with another lorry of mass 3,000 kilograms. Put the mass above 3,000 kilograms, and that's moving at 4.5 meters per second, but it's in the opposite direction. And then momentum afterwards, so they combine. So the mass is 4,200 kilograms, and then we just need the velocity. So momentum before equals momentum after. So the momentum is 1,200 times 20 plus 3,000 times 4.5 equals 4,200 times the velocity, which is v, which is what we're going to find out. So 1200 times 20 is 24,000, plus 3,000 times 4.5 is 13,500. But be careful with the plus, because it's plus but it's in the opposite direction, so a plus and a negative is actually just a negative. And that'll be equal to the 4,200 times v. So we just need to do 24,000 minus 13,500 and then divide by 4,200. So that would be 10,500 divided by 4,200, which gives a velocity of plus 2.5 meters per second. The 2.5, the plus, sorry, means that it's going to the right, as we took right as positive with this one. The 4.5 meters per second we took as negative, as it was moving in the opposite direction. So the plus means that the system would in fact be moving 2.5 meters per second to the right. Hopefully that's okay. Let's move on. So if you want to have a look at this one, please do. Just pause. A car of mass 580 kilograms collides with the rear of a stationary van of mass 1200 kilos. Following the collision, the van moves with a velocity of 6.2 meters per second, and the car recoils in the opposite direction with a velocity of 1.6 meters per second. What is the initial speed of the car? So let's try and map out what's happening here. So the car, which has a mass of 580 kilograms and a velocity which is unknown, which we're going to find out, collides with the rear of a stationary van, so 1200 kilograms, velocity of 0. So that's the total momentum before is equal to the total linear momentum after the collision. So we've got the car of mass 580 kilograms. And that actually moves to the left with a velocity of 1.6. So when we do our calculation, that will be negative 1.6 because we're going to take the right as positive. Plus the van. So the van has got 1200 kilos. And its velocity is 6.2 meters per second. So then we just need to look at the momentum of everything in this system. So I'll make a grid. So we've got 580 times V plus 1200 times nothing, so plus 0, equals, then we've got 580 times minus 1.6, which gives minus 928, plus 1200 times 6.2, which is 7,440. So we just need to rearrange this to find V. So we've got 580V equals, we've got 7,440 minus 928, which gives 6,512. So V is equal to 6,512 divided by 580, which gives a velocity of 11.2 meters per second. The value is positive, so that means that it's moving off to the right. So let's just do one more question. Pretty straightforward. Hopefully that went okay. If you need to redo any of this, just redo it, just for more practice and to ensure that you know the technique in full. So one more question. Multiple choice. Which line A to D in the table correctly shows what is conserved in an elastic collision? So the answer will be D. Because in an elastic collision, mass, momentum, kinetic energy and total energy is conserved. If it was an inelastic collision, the answer would be C, because in an inelastic collision, everything is conserved aside from the kinetic energy. So that's the conservation of linear momentum. Hopefully that's helped, and I'll speak to you soon. Thank you.